Let's look at a few examples of solving equations that have exponentials in them. The general idea is to use a logarithm. Whenever you have an equation that has the variable trapped inside of an exponent, like in this one, we're going to use a logarithm at some point to extract the variable from that exponent. In this particular equation, 2 to the 3x equals 32, we have the exponential part of the equation isolated already, and so we can immediately use a logarithm. Whenever you use a logarithm, you have to decide on what base to use for your logarithm. Since this exponential is base 2, it seems like using log base 2 would be a good idea. So let's hit both sides of this equation with log base 2 on the left and log base 2 on the right. Okay, so on the right-hand side, log base 2 of 32, let's see, 32 is 2, 4, 8, 16, 32. So 32 is 2 to the 5th, so log base 2 of 32 is 5. On the left-hand side, we have a composition of functions here. We have the 2 to the something function, and inside of that is 3x. And on the outside, we have the logarithm base 2 function. But these two functions are inverse functions of each other, so they undo each other and just leave us with the inside, which is 3x. And now we can finish solving for x. We can just divide both sides by 3. So x is 5/3. So whenever you have an equation where the variable is trapped in an exponent, you're going to use a logarithm at some point to solve for that variable. But you might not use the logarithm immediately. So let's look at this example. We're going to solve for x again, and this time the equation is 2 times 5 to the x plus 4 equals 16. So if we tried to use a logarithm right away, you can see that the left-hand side, we would have some logarithm with this entire left-hand side in that logarithm. And this is a real mess to have inside of a logarithm, so that doesn't seem like such a great idea. Instead, what we'll do is, if you keep your eye on the part of the equation that has an exponential, we need to isolate this part of the equation first. Once we've isolated the part of the equation that has the exponential, then we can use a logarithm to extract the variable. So let's isolate the 5 to the x part. So the first thing we're going to need to do is subtract 4 from both sides. We get 2 times 5 to the x equals 16. Now we can divide both sides by 2. And we get 5 to the x equals 8. Now we've isolated the exponential part of the equation. Now finally we're ready to use a logarithm. Like with the last example, we need to decide on a base for our logarithm. And we can use base 5 since we have an exponential base 5. Okay, on the left-hand side, again we have a composition of log base 5 and exponential base 5. Those are inverse functions, so they undo each other, and we're just left with whatever is all the way inside here. And for this one, it's just x. And on the right-hand side, we have log base 5 of 8. All right, so log base 5 of 8 is a perfectly good answer if you're after a mathematically perfect answer. But if what you want to know is approximately how big x is, log base 5 of 8 doesn't tell you that much, so you might want a decimal approximation. But remember, most scientific calculators don't have a logarithm button that can have any base. You have two bases to choose from, base 10 or base e, but you can always use the change of base formula to switch to one of those two bases. Let's switch to base e just because it's math class and we like base e. So this is going to give us natural log of 8 over natural log of 5 And then finally, we can punch this all into a calculator. So let's see, natural log of 8 divided by natural log of 5. I get about 1.292. And here I should have, this is actually exactly equal and this one is only approximate. Okay, so the moral of the story here is, if you have an equation with an exponential in it, first isolate the exponential and then use a logarithm to get access to the exponent. Okay, so let's see how this works for an application. Let's figure out how long does it take for $10,000 to grow into $15,000 if it earns 5% annual interest compounded continuously. So this phrase compounded continuously, that's an important phrase because we know that deposits that compounded continuously, the balance of that account after n years, we figured out a formula for it. It's the initial value of the account times e to the r times n. And r in this case is the interest rate. And n in this formula is the number of years. And this does assume that your interest rate is annual, which ours is. Okay, so we want the ending balance of this account to be $15,000. A is the beginning value of the account, and that's 10,000 times e to the interest rate. And remember, when you use these interest formulas, you always need to write your interest rate as a decimal, not as a percent. So 0.05 times n. And so we need to solve this equation for n. You can see, since the variable is trapped in the exponent, we're going to have to use the strategies that we figured out to solve this equation. So first, isolate the exponential part. So we'll divide both sides by 10,000. That gives us, on the left-hand side, turns out this is 3/2. On the right-hand side is e to the 0.05n. All right, now we've isolated the exponential part, so we're ready to take a logarithm. And since we have an exponential base e, seems like using natural log would be a good idea. Okay, on the left-hand side, this is just natural log 3/2. We can dump that into a calculator at the end if we want to. And on the right-hand side, again, we have a logarithm and an exponential with the same base. These are inverse functions, so they undo each other. And on the right-hand side, we get 0.05n. And finally, just finish solving for n. We'll just divide both sides by 0.05. And we get natural log of 3/2 over 0.05, and that's n. And again, if you actually want to know about what this number is, you can dump it into a calculator. So natural log of 1.5 divided by 0.05, that's about 8.11. And this is going to be in years. So that initial $10,000 grows into $15,000 after 8.1 years. All right, one final example. Let's solve this equation for x. So 3x times e to the 2x minus 12 times e to the 2x equals 0. So this one looks a lot more complicated, but it's important not to get so wrapped up in the fact that there are exponentials showing up here that you forget all of the other algebra you already know. So if you think about all of the other algebra you already know, you might notice, hey, both terms on the left have e to the x. Maybe we should factor that e to the x out. So let's do that. I'm sorry, e to the 2x. So factor out e to the 2x. So e to the 2x times 3x minus 12 equals 0. And, if you think back to all of the equations we solved with polynomials, when you have a 0 on one side of the equation and a product on the left, one of these two things has to be 0. But the exponential e to the 2x, this is never 0. There's no x you can put in here that would make e to this power be 0. And so this first part of the left-hand side doesn't actually contribute any solutions. All we need to worry about is the second part, 3x minus 12. So we'll finish solving 3x minus 12 equals 0. Move the 12 over, divide by 3. X is 4. Another way to think about what just happened is we can divide this entire equation by e to the 2x, like this. Now, dividing both sides of an equation by something that has the variable in it can cause problems because you might accidentally be dividing by 0, but e to the 2x is never 0, and so dividing by e to the 2x is perfectly safe. On the left-hand side, the e to the 2x simplifies away. On the right-hand side, of course, you still get 0. And so again, we're solving the same linear equation, 3x minus 12 equals 0.